Uh, Welcome again to another Kent seminar. Today we have Dr. Armelle Chabot. She's joining us from France. So again, we really appreciate the effort because right now it might be something 9 p.m. over there. So thank you very much for being with us today. So I'm gonna give her short bio and then we can get started. So Dr. Armelle Chabot has been at Gustave Eiffel University, the former IFSTAR and LCPC, since 1999. She obtained her master's degree in structures and materials mechanical sciences from the Université Pierre et Marie Curie in Paris. She obtained her PhD at the École des Ponts Paris Tech and research supervision habilitation from the University of Nantes. At Gustave Eiffel University and through international collaborations with various organizations, such as RILEM and TRB, her research is focused on providing experimental tools to define the interface rupture resistance between pavement layers and calculation tools for diagnosing damaged road structures and adapting them to new uses and unprecedented climatic context. Let's give Professor Chabot a round of applause and thank you for being with us today.
Thank you very much to give me this opportunity to present some work I have done since many years. And I would like to again thanks ICT team for this invitation. So my talk will be about mechanics and analysis of debonding in pavements. First of all, I have to present a little bit where I'm working. So in France and in the west part of France, in Nantes, we have a campus that is quite big outside the city. I guess it's like where you are in Ventoux. In this campus, it's quite old. It has been created in 1975, and I joined it in 1999 for pavement. At that time, it was the biggest campus in France who were dealing with pavement. We have a big test track for testing skiing resistance, but I am in the team who is dealing with accelerated pavement testing, and it was a great honor the last 2 years to invite the whole APT conference and TRB member who could come in France or not due to COVID. So we have a carousel, is the fastest APT devices in the world. We can, the speed can go up to 100 km per hour. Usually we use it with a limited speed at 72 km per hour. That is supposed to be the average speed in France for our design method. We have also a little fabac machine. We can test with this machine only 2 meters long. And with the carousel, we can test 100 meters long. We have a YouTuber after the conference who came and visited us and did an interview to my colleague Pierre Ornish. And if you would like to have more knowledge on the carousel, I recommend to watch the YouTube interview he has done. I was very surprised. There is 4 million of people who have reached, who have seen this interview. My talk will be separate in 3 parts. In the first one, I would like to precise that I'm not dealing with micromechanics. and in that part, I will define what is interface and pavement, and for debonding. So for me, pavement, it's different layers that are superimposed on top of soil, and each one of them have its own behavior. Interface is the place, the limit between two materials. In that model, we developed early in 2003 with my colleague from ENPC, Diony Duhamel. We developed the way to have viscoelastic materials such as asphalt material is, and we put in our equation the Riet-Sayet model that in France we are using. And with a fast Fourier transform, we could and we can model the pavement structure, saying that the soil is half space in the modeling. When Olivier Chupin came for his postdoc first, we developed the modeling and the tool in order to have the possibility to put sliding interfaces. And in the code, the Viscoroad software we were sharing for free for everyone who wants to get it. We are now trying to put the software on web. It will be ready next summer, with this possibility to have access to perfect sliding interface. So in the figure, you can see that the strain among the depths are different per layer. You can see that for the two first layers that are supposed to be asphalt layer, due to the low speed we choose in that example, the distribution of the strain is not linear. And for the other layer, it is that they are elastic. And if we take into account of sliding interface, above the interface and below, you can see that there is a lot of differences between this, the value of this strain. This is very interesting to have this. When we are doing accelerated pavement testing, we are putting strain gauges, and with them we can see from a reference point what's happening. But it's not easy, because it is supposed to know perfectly the temperature of each material and the behavior of each material. If you look on the top of the pavement, sliding interface will make more deflection, and it will play a role on pavement life. But actually, we need more than a modeling and strain gauges or things that are upper the pavement. That's why, with my colleagues from Direction Générale de l'Aviation Civile, Michael Broutin, and my PhD student that did her postdoc there, we use the ovidization system that was developed by my colleague from LCPC in the past for roads, and we adapt this device for airfield pavement. And so this device is making with sensor that are measuring the deformation, the diameter deformation of the hole when you have a load or you use a heavy weight deflectometer. So we developed a first specimen, and at DGRC they have now improved a lot this system, and I hope they will present you this later. We couldn't use Visco route because there is a hold, and in the software Visco route, we are assuming that the behavior of each layer are the same. It's the same kind of modeling that Burmester model elastic that is used in our French design method, and I think in America you are using this for Ken layer software. And we show for one experiment that measuring and getting access to what we had from 3D frame modeling for this experiment, the interface at this location was fully bonded. The main problem is for pavement, it's not only a full bond or full debonding, it's more complex. Here on the upper part of the slide, my colleagues from the past took extract B layers from airfield pavement at that time where we developed Airbus A380. At the time it was named A3XX. And you can see, it's well known, that if there is a good bond, due to bending effect of loads, you have tension stress at the bottom, and the crack is coming from the bottom up to the pavement. But when I'm saying up to the pavement, it reaches the interface. And here, we need to have the behavior of the interface and the criteria in the material and in the interface in order to see if the crack will propagate among the interface or up to the layer. So my knowledge is more on that, saying that when you have 3 edges in the multi-layer, you cannot deal with only 2D structural modeling. You need to have 3D. For this example, if you take 2 layers and you do tension test, you will see that there is a sliding at the interface, but at the edge, you have also sliding in this out of plane direction. It is also well known from composite field that when you have a bending test, you may assume to have a crack and normal interface trace and out of plane shear interface stress that are quite zero far from the edge, but at the edge there is critical stresses. And dealing with failure, we need to have some tools that are able to model and test, that are able to give this information. That is why in my PhD thesis a long time ago, I studied that, and dealing with failure. Everybody knows that if you deal with a homogeneous material, you will have a singularity of a crack. But for B material, when you have a crack with at the interface, mathematically and mechanically, the lambda coefficient that is normally 1/2, half, it's a complex number. So there is no physical meaning. And a lot of people have worked for composite field on that and developed their own model. In my PhD, I developed a family of modeling that are resting to the fact of dealing with multi-layers. It's plates. So I try to use plates modeling that I have improved. And saying that, I assume with my advisor, of course, that the 3D stress can be written as a polynomial approximation per layer E in Z. Z is the out of plane direction. saying that it's possible in Ellinger-Reisner formulation because it's leading to a mixed mode, a mixed formulation. It's possible to solve the problem. As we know everything in Z, we only have to deal with solving a problem dealing with X and Y that are the coordinates of each layer. To do so, each factor of this polynomial approximation, we choose to have them like a general force of plates of Elegant-Reisner that I'm showing here. So for each layer E, we don't have Z, but we have E, the name of the layer. We have the sigma, 3D sigma, that is developed as a polynomial expression of N, Q, and M that are the Ellinger-Reisner, the Manning generalized force of plates. And we assume in that modeling that the interface force between the two layers are the exact expression of shear, out-of-plane shear stresses and normal stresses that we call tau and nu. And for interface between layer E and layer E plus 1, it's in the modeling, we don't have Z, but we have each component have its own index E. So we know that if E is 2, it's the layer 2. And if we have interface between layer 2 and layer 3, it will be nu or tau 2 question mark 3. So when I came at that time, it was LCPC, not Gustave Eiffel. I tried to develop this model for pavement. Pavement has a soil. So lastly, I chose to use Winkler soil because it's very simple to assume that it's a kind of spring. And in the composite example I gave with this cohort, dealing with elastic material that time, but with vertical crack, you can see here in that figure that the interface between layer 2 and layer 3 in the direction like this, it's opening. When the rods are close to the crack, you can see that the value of this interface are becoming bigger and bigger. You can do that with 3D fine modeling, but if you improve the mesh and you do it thinner and thinner, you will find that you will never converge. With that modeling, it's fixed. So we can compute this and solve this numerically, but at the end, it's reaching a value. That is very nice if we want to use that modeling in dealing with a criteria. I just want you to see this illustration. Lately, we are also working with electrified roads, and for induction problem, it's a slab that you put inside the pavement. And I was part of a Shen PhD jury and was very surprised not to have so much information about the bond between the slab and the pavement. And that's why I took a student, Pawan Deep, who improved the M45N model in order to take into account that other material in one layer. And of course, it's obvious, but if you put a rigid box in an asphalt layer that its modulus is not so strong with the temperature and the load and whatever, I was recommending to maybe deal with. At that time, the box was made with cement concrete, to have a cement concrete layer on top of asphalt in order to reduce these stresses between the box and the layers. That's it for the modeling, but I will come back later. I have mentioned that we need some tests and failure criteria. So that is why I will present lab characterization. I have the chance to attend in 21 the cracking in pavement group and the meeting in Brussels, where I have seen for my first time and Imad Al-Kadi, Professor Al-Kadi. And it was a great meeting with also André Molenaar from Delft University and my colleague from Limoges. And at that time, we were trying to organize the Cracking in Pavement conference in Limoges. And we worked after with all these colleagues in order to have more knowledge on cracking. And Imad organized the CP conference in Chicago in 2008. And during my stay at Urbana-Champaign in 2010, I had the opportunity with Bill Butler to start a new technical committee of RILAME. And I push a lot to have a technical committee, not only dealing with cracking in pavement, but also in debonding, and not only in asphalt pavement, but also with composite pavements. In that TC, we had a free task group, TG, and in the TG2 with Christophe Petit, Alexandra Destré from BRCC from Bruxelles, BRRC from Bruxelles, and Christian Marab from EMPA. We published a state of the art in the state of the art chapter 3. We published all the standard and research tests that was existing in order to solve this problem at that time. So it was published in 2018, and we published some recommendation saying that it's a need to have a lot of repetition in order to have access to the knowledge. So here I will show you what I have done in my lab. First of all, I work also on the bond for ultra-thin white topping. At that time when I came, it was not a question to deal with the bond between asphalt layers. And it was something we don't have to deal. So I work on that. And we developed a test, a 4-point bending test, where I use my modeling in order to design the test. First of all, we choose at the end to have a non-symmetrical test in order to localize the debonding in one edge and not in one of the two edges. We follow the debonding with DIC. And here in this figure, you can see between the elastic equivalent modeling between the two layers, asphalt that is black layer 1 and cement concrete layer 2. You have a competition between the tension stresses at the bottom of layer 2, that is supposed to be cement concrete, on point B, A, B, C, D, and the interface shear and normal stresses. so it was very nice to have this opportunity, and dealing with energy release rate, we demonstrate that it was possible to have analytical solutions, and this energy release rate, we could separate mode 1 and mode 2, and it was very interesting to get access to that. And to be sure that it was okay, I needed to have another test in pure mode in order to try to see if I can get access to I can confirm the question I had. So that's why I chose to develop and adapt the wedge pitting tests, likely with the ANR project we have and Maïssa Gerbi PhD thesis. But I wanted not to test the debonding and the interface with material that have been constructed in the lab. I wanted to have them, getting them from a real world test track. So we did that. And to respect the recommendation Professor Chegg did, in that project also we were testing interface with grid. It was a need to have a big specimen, and with 10 centimeters thickness. And to do so, it was not possible to build this 10 centimeter layer in only one layer. So we built this with 2 sub-layers. I will show you only some results dealing with reference material only with asphalt, but built in with with 4 layers. And here we used digital image correlation for specimens who were working very well. It was cool to see the location of the crack. I chose the wedge pitting test because it's a test that is quite stable with the propagation of crack in comparison to the 4-point bending test I used before in Manitou Hoon PhD thesis. I push my colleagues to not have only 2 or 3 tests, but more than 9 or 10 tests, as we recommend in RILEM. And here you can see that dealing with only 9 to 10 tests, you have a lot of differences. So I try to explore, and I start that when Ishan Dowe, that is in our room, came and visit us in Nantes, and also I couldn't use my modeling because of the crack that is not brittle, and you have to deal with the ductile material. So that is why I wanted to compare what you have with coincident model in Abacus with Ishan, that he has knowledge, and what my colleague from the past did when I did my PhD in composite. And I have the chance to have Laurent Gornet in Nantes also, and he put that modeling in a Castan free FEM code. And in this modeling that is called ViscoHunt, it's possible to take into account a delay of the material, that for us it's a viscoelasticity, and to take into account of several modes like mode 1 and mixed mode. We did that, for 2 tests with a student from École Centrale Nantes. And for the test in green that didn't work, actually we have some problem with intermediate interface during the test, and we saw debondings. I repeat that these 4 layers are supposed to be the same, but due to the construction and the air void content, actually we test this specimen in order to see what was the air void content of each sub-layer. And supposing with in the French design method, we are assuming that the modulus is less with air void content, is reduced due to air void content. We take this into account in this FAME viscount model, and we explain activate the mix mode at this sublayer interface. We explain the result we get. So the work is not finished. But in that time, we are now Gustave Eiffel. We are dealing with cities, and cities, it's actually a big topic for France. And also climate evolution is a big topic. So in my third part, I will quickly present what we are doing. You can see last year, it was the climate and the temperature during August was incredible. And if you look at the prevision, everybody are telling that all the prediction are confirmed. We are all expecting that it's not the case, but for now it is. And in cities, in 2020, there was 80% of French people who are living in cities. Nowadays, in the world, there is more than half of the population who are living in cities. And it's well known that the construction, when you are covering the soil with material, you increase the heat. And here you've got in the curve the differences of temperature between outside the city of Nantes and inside the city. So that is why there is several solutions. Of course, a lot of people are dealing with this, like in University of Davis since the beginning of 2000, I guess. Saying that if you are using asphalt, it's a black color, that is not a good option dealing with temperature. So some people are trying to put all different colors in the pavement. Alexandra Destre from BRC that worked a lot with us at RINEM have a great knowledge on that, and it's not so simple to deal with the color of the pavement, because people have to accept the color. The color, if you are using a white color, it reflects the light to the building, and it reflects the light to the eyes. It has to be acceptable, and you can have dust on top. So it's not so easy to propose this. So that's why there was a lot of people who are working on that, trying to find some solution. And in Paris, a lot of people are trying to develop the fact that we don't have to cover the road with asphalt, and we are coming back to granular and cover with water during the evening. But you need to have water in the city to do that. And also, some people preconize to have vegetations and take care of trees and the shadow and trees. I like this very much, and I've seen I took some picture when I came in 2010 at Urbana Champagne of trees because I was very impressed of the trees you have in your campus, and you can see the tree roots, and we have to deal with all of that in the pavement. So with Ishandowe, we hire a PhD student, Selector Moss, who started his PhD in co-tutel with our two lab in 2022. He will present ISAP what he have done for the literature review, so I will not go further. For those who will attend the conference, if you are interested, don't hesitate to listen to what he will present. Come back to bending case and discontinuity for pavements. Of course, if you have a big soil, you have less problem, and the problem you have is only on the top of the pavement. If you don't have, you can have some troubles. Anyway, I will show you in the past, before the M4 5N modeling with Winkler spring, I first developed with Boussinet modeling. At that time, we model the effect of the coefficient of thermal expansion in a cement concrete layer or a material treated with hydraulic material. And we shown, of course, between, at that time, the soil and this layer. We compare also with 3D modeling. We show that you may have debonding, of course. So we will, in that topic, we will improve that for the upper layer. Doing that, we need to have access to the coefficient of thermal expansion of each material, but it's not obvious. And here is a zoom on what you can have without effect of this coefficient, but only the ratio of modules with that modeling. And if you have the green dash point curve, is a focus at the interface between layer 2 and layer 3, focus close to the vertical crack. And if you have the same material between layer 2 and layer 3, of course, you will have an impact due to the vertical crack. But if the material is different and more different, is a red curve, you will get differences. And again, with my modeling, the stress are finite. There is no stress going up to infinity. It means for lab test, we have to deal with that. We have to see which type of forces we apply on our specimen. Here I can show you also what we have done in the past, dealing also with ultra-thin white topping. I guess you had a nice presentation from the colleague from Julie van der Bosch from University of Pittsburgh, that has huge knowledge on that. But in 2004, we test the joint of ultra-thin white topping. And here you can see the differences of debonding we get from material that was tested during winter season and summer seasons. And doing this, ultra-thin white topping is a cement concrete that casts the whole of asphalt material. We can also deal with interface, not only interface. You can assume that you can have a free material. And the third one is intermediate between the cement concrete, intermediate material between the cement concrete and asphalt material. Last, doing with climate change, we have to deal with water. So that's why for the 4-point bonding, I test this in a bath with Manitou. And we show that we have differences between testing the material, the bilayers into a bath and without water. So we cannot ignore that. And for the wave splitting test, it was worst for intermediate debonding. So that's why we need to progress on that. And my question is also, we have accepted in France a national project on urban heat island. It's quite new. And we have to work more on people who are dealing with cities because they are improving the cities. They have a lot of ideas, and with their ideas, they are putting things inside the roads. So we cannot ignore that. And we need to have good modeling, not only pure multi-layer modeling in order to have response of the durability of such systems. So for my conclusion, for the first part, it's a need to get data coming from the field for the different loads, different temperature and water, the geometries, like I said. It's a need to have repeated testing results. I didn't talk about the size of the specimen, but of course, if you are dealing with cracking, it's a question. Cement concrete field have a lot of knowledge, of course, on that, and we don't, in my sense, we ignore a little bit that for asphalt. It's a pity. We cannot ignore water effect. If we test and we are using tools that are giving us some results in 2D, but these results are made in specimens that are 3D, so we have to be very careful on the results we are having. And for urban heat island problem, of course, we have to work with urban planning researcher that are creating some new pavements and new configuration of the roads. And for that, it's a multi-material program, like we are saying with Ishan, and we cannot ignore the condition, the boundary condition. Of course, here, dealing with trees and vegetation, we have also to be careful in cities with wind. So, and be careful on the roof of the trees in order to avoid such events in cities. So thank you for your attention, and I will be pleased to answer to your question.
Thank you, Professor Chabot. I will open the stage for questions. Okay, we have some questions here, so you can start.
Hi. Thank you, Professor. That was a great presentation. I had a doubt with the urban heat island part of the presentation. So when we propose to use lighter pavements in place of asphalt pavements, how do we plan to, reduce the heat that is coming from this, like when the pavements reflect, how do we plan to control those radiations and, keep the heat in control? Like, I can't think of it right.
Yeah. So it's not. I have not a perfect answer, because in the city, when we are starting the discussion, it depends when you are putting the color pavement, and meaning that if the roads are made with buildings that are close together, it's not a good idea to have such reflect paint or color, because you reflect the heat to the building and you heat the building. So dealing with this, you have in the city several solutions for several districts is what we are dealing with. And in BRC, they had some work, very nice work, also in order to see the durability of the paint or the color of the pavement. And in France also some industrial partners are trying to develop that because it's not so obvious to have a color that is permanent with time. And so I don't know if I answer to your question, but that is the thing we are trying to discuss with people. We preconize some colors also. You cannot put pink color or maybe a yellow color or red color. Alexandra Destré did also mention that psychology, in the psychology part, people are not ready to have the soil paint with every type of color. Whatever the color is and used in the city, for me, it's not something I will deal a lot on that, because usually you put also color in some roads in the city that are not loading with a huge load like buses or tramway. It's a pedestrian area or for cyclic bicycle area. It's also for car. So from a pavement point of view, it's not structural a problem. It's not that thing that I will more focus in the future on.
Sure. Thank you, Professor.
Any more questions in the room? So it's strategic. Professor Chabot, we want to thank you again for being with us. Again, it's quite late there, so thank you very much, and let's thank Professor again for.
Thank you very much for this invitation.
Thank you, Armelle.
And I hope to meet you, all of you, or some of you at ISAP.
Yeah.
In June.
See ya.
See you, Imad. Thank you again.
Yeah. See ya.
Bye-bye.
Oh,